Hi, my name is Liz Thompson, and this is a quick video on an introduction to queuing theory, sort of the basics of using math in industrial engineering. Queuing theory is also a part of operations research. So I'm going to explain what queuing theory is in the simplest form and the simplest aspects of it. I'm also going to then work through an example and show how it might be used in analysis. So queuing theory is the concept of there's items, people or parts or anything that needs to be processed by a server who does some work that takes some time on the items or with the people. So the way we usually conceptualize this is the three dots on the left is what I'm saying are the items that need to be served. They start to move towards the server and form a line. And then as the server is available, one person in the line or one item in the line is served by the server and then exits the system. So we call this line a queue, and that's what we call queuing theory. And then the whole system is we define as the line and the server. So we don't include the items that are traveling to the systems. We draw the system this way. One of the important things about queuing theory is to really define the type of queue. You can imagine there's all kinds of different types of queue. This particular type of queue is a one server, one line, first in, first out. So that means the first items to get in the line are the next ones that are going to be processed. So we travel through the line this way. Now, there's all kinds of other types of configurations for queuing theory. There could be multiple server, one line, first in, first out. There could be multiple server, one line, last in, first out. So instead of going to the end of the line, the next item goes to the front of the line. Now, all of those indicate a different kinds of calculation. But the calculations I'm going to talk about right now are a one server, one line, last in, first out type queue. And in this particular orientation, what we do is we define a lambda and a mu, which is the lambda is the arrival rates. And the arrival rates, what we say is lambda is an expected time of arrival per hour. But these vary. There's a distribution associated with it. And we define the distribution as exponential. So that looks sort of like this, where we have a lambda that is the expected value, but it's distributed over time. Mu is an indication of service rate, and there's also an expected value, and that varies over time. So we can think about these things as distributions. Like sometimes there's two people that arrive together, and then sometimes there's like 10 minutes until the next person arrives. And then in the service rate, sometimes the service takes 10 seconds and sometimes it takes 3 minutes. So there's a variety, a distribution of the service rate. So what we do is we have these lambda and mu where the arrivals are expressed in items per unit time and the service is also expressed in items per unit time. So the input in a queuing system is the queuing type, which in this case we have a one line, one server, first in, first out. And then we also have an arrival rate and we have a service rate. And that's kind of all we need. And then through some really kind of neat math that you will understand if you actually study this in depth, we can actually describe things about the system in pretty simple equations and examples of the ways that we can describe the system. And there's actually a lot of ways to describe the system, but examples are we can talk about the capacity utilization, we can talk about the number of people in the system, we can talk about the time that people or items. We can talk about the time in the system. So simple equations like the capacity utilization is lambda over mu, pretty simple equation. The number of people or number of items in the system is rho, or the capacity utilization, divided by 1 minus rho. And then the waiting time in the system is the number of people in the system divided by lambda. So we have these pretty simple equations that are actually complex to derive, but they're based on distribution of arrival rates and service time. So it's really kind of cool that you can describe the system in this way. So I'm going to go through a really quick example of this. Well, not maybe really quick. I'm going to go through an example. So in this example, it's parts are arriving to a milling machine, and they're going to be processed, and they arrive at a rate of 100 per hour. This arrival follows a Poisson process, and the processing time for the items on the mill have an expected time of processing of 30 seconds, and the processing times are exponentially distributed. So the first question is, what's the capacity utilization of the machine? That means how much of the time the machine is being used. And then what are the number of items in the system, both waiting and processing? And what is the time in the system for each part? Like how long are the items going to be waiting there? And if each part is large with a footprint of 2 square feet, how much space should you assign to the waiting area? So these are some of the questions we can get from this simple queuing problem. So in this queuing problem, we initially can just establish lambda, which is the arrival rate, as 100 units per hour. The mu is a little bit harder because what we see is it takes 30 seconds to process the part. That's the service time. And we have to make sure that the mu is actually in units per hour, and the 30 seconds per part is actually seconds per part, which is not the right units. So we have to take into account that there's 60 seconds in a minute and 60 minutes in an hour. So that means it takes 0.0083 hours to process a unit, but still that's not quite the right units for mu. The right units per mu is 1 unit per 0.0083 hours, which means 120 units per hour. So that's our lambda values that we got. So now we can do the calculation. That's the mu value. So now we can do the calculation of capacity utilization by taking just lambda over mu for rho, and we get 100 over 120, which gives us 83%, or 0.83 as the capacity utilization. That means the machine is running 83% of the time. That's pretty good. That's a pretty good utilization. So the next thing we then can do is we can calculate out the length or the number of items in the system. So the system is both waiting and processing, and that's going to be rho divided by 1 minus rho. And so that calculation says there's going to be 4.9 items in the system. So about 5 units are going to be waiting. There'll be 4 units waiting, and then there'll be 1 being processed. And then the next thing we can calculate is the waiting in the system, the time waiting in the system. So that's L of S divided by lambda. And so that's 4.9 divided by 100, or 0.049 hours, or about 3 minutes in the system. And that gives us an idea of how quickly things are being processed. The next thing we might want to do is calculate what's the area that we should be waiting. And I assumed there would be 4.9 units waiting, but actually one of those is probably on the machine, so it would maybe be 3.9. But either way, we make that assumption that 4.9 times 2 square feet means that we need about 10 square feet available. So we would, if we were doing a facilities design, we would allocate a space that is about 10 square feet. Now, I hope that gives you an idea of some of the ways that we can use queuing theory to get some good analysis going.